Hi, folks. The next skill we need to learn is solving equations by graphing. And the sort of equations that we're looking at today are a little bit complicated. We've got, like in this example, we've got x terms on both sides of the equation. But if you remember, we actually learned how to solve these types of equations algebraically back in chapter one. Um, so why are these appearing again? Well, what we're going to do today is we're going to take each half of this equation, each side of this equation, and make a separate equation out of that. So for instance, I'm going to say f of x equals negative x plus 1. So I've taken the left side of this equation and made a separate equation out of it. And now I'm going to do the same thing for the right side of the equation. I'm going to say g of x equals 2x minus 5. And what I've actually done here is created a system of equations, just like we've talked about in the previous 4 sections of this chapter. Now, the reason for doing this when we already know how to do it algebraically is perhaps seems silly, but if you get more complicated examples, sometimes graphing is the easiest way to evaluate an equation, even if you so if you don't know how to do it algebraically, you can do it graphically instead. So, how do we use a graph to solve this equation? We just plot it like it is a equation. So I'm going to take this purple graph here. The y-intercept is at 1, and my slope is -1, even though the 1 isn't written there, it is implied. And so that -1 slope means when I go up 1, I go left 1. Or when I go up 1, I go left 1 again. Or when I go down 1, I go right 1. So remember, -1 is the same as -1 over 1, or it's the same as 1 over -1. And that's rise over run. So when I go down 1, I go right 1. And continue the pattern out this way until we get to the end of the graph. And so now if I plot the line for this, that is my equation for f of x equals negative x plus 1. Let's graph the red equation now, where the y-intercept is -5 and my slope is 2. So when I go up 2, I go right 1 with this positive 2 slope. Up 2, 1, up 2, right 1. And my equation looks like this. And I can see that I do have an intersection point right here at the point 2 comma -1. So kind of as we've done with systems of equations up to this point, you find the intersection point, and that ordered pair is the solution to your system of equations. Now, in this example, this didn't start off as a system of equations, so our answer does not need to be an ordered pair. If you look back at the original equation, there are only x values in this equation. There are no y values. Therefore, the only important part of this ordered pair is the x value. Actually, x equals 2 is the solution to this equation. There is no y value in this for this solution because there is no y in the original equation. So let's look at a more complicated example here and why we might want to use this method. Once again, I'm going to take each side of the equation and make a separate equation out of it. So f of x is going to equal the absolute value of x plus 1. And I'll do the same thing for the right side of the equation. G of x is the absolute value of 2x minus 4. And to uh, kind of go about graphing these, you may remember that this when you have a plus 1 inside the parentheses, inside the absolute value, that indicates a horizontal shift. Uh, you're changing the input values. And because you're changing the input values, because it's inside the parentheses or inside the absolute value, then the shift is the opposite of what you expect it to be. So this is actually going to be a shift to the left one. Even though this is plus one, we're actually going to move to the left one with this graph. So our absolute value graph is going to look like this. And let me draw this in here and draw this in here. And so my purple graph will look approximately like this. Because there is a coefficient in front of x inside the absolute value, this is a more complicated situation to graph. And I do recommend kind of creating a data table when you have a situation like this of different input values and their corresponding output values to help you graph this, because there will be a horizontal shrink um, by a factor of 1/2. Remember, when the change occurs inside the absolute value brackets or parentheses, the change is to the input value. So the change is opposite what you expect. Even though it looks like we're multiplying by 2, really we're multiplying by 1/2. So we're creating a shrink. And there will be a horizontal shift to the right, but it will not be a shift of 4 because we're multiplying by 2. This is actually going to end up being a shift to the right of 2. Our vertex will be here. As I said, this is more complicated than the examples we did in class. Really, the easiest way to do this is by doing a input-output table. So I'll just test a few 0, 1, 2, 3, 4. I'll test a few x values near where I think the vertex might be. And then find the output value. So if I input 0, 0 times 2 is 0, minus 4 is negative 4, but I'm taking the absolute value of it, so it's not negative 4 anymore, it's positive 4. 1 times 2 is 2, minus 4 is negative 2, but you take the absolute value and that's positive 2. 2 times 2 is 4, minus 4 is 0. 3 times 2 is 6, minus 4 is 2. And 2 times 4 is 8, minus 4 is 4. So I end up with points like this on my graph. So you can see there's a slope of 2, a negative 2 in that direction, and then a slope of positive 2 in this direction where I can continue graphing. And my absolute value graph looks like this. And you can see that there are 2 points of intersection here. Now, this is actually something we observed in chapter 1 when we were solving absolute value equations. Sometimes there were 2 solutions, sometimes there were 0 solutions, sometimes there was 1 solution. And we can, by graphing, we can actually visualize why this is true. There are 2 solutions to this particular system. But you can imagine other shapes with absolute value graphs, like perhaps like nested V's, which might never intersect like that, or perhaps the V-shaped where it's flipped across the x-axis and they don't intersect for that reason. And you can imagine other scenarios where the absolute value just intersects another graph just once. So for instance, if I have overlapping V's like this, where the slopes are the same, so this branch and this branch are parallel, so they don't intersect with each other, but does intersect with this branch of the absolute value equation here. So by graphing, we're able to visualize whether these absolute value equations have 0 or 1 or 2 solutions, depending on the situation. Now, how do we interpret those solution points? Remember, each intersection point gives us an ordered pair. So here I have the ordered pair 1, 2, and here I have the ordered pair 5, 6. But if we look at the original equation, there are no y's in this equation. So we don't need to know the y values. We just need to know that the solutions are when x equals 1 and when x equals 5, that those are both solutions to this system of equations. So let's look at a real world example of this strategy. In 2020, Glacier A had an area of about 40 square miles, and Glacier B had an area of about 32 square miles. You estimate that Glacier A will melt at a rate of 2 square miles per decade, and Glacier B will melt at a rate of 0.25 square miles per decade. In what year will the areas of the glaciers be the same? So, here I want to know a year. I want to know how much time is passing. And it looks like I'm counting time from the year 2020 is my starting time. So I'll be counting time from that original year. And I have time, I'm seem to be measuring time in decades. I'm talking about how many square miles are being lost per decade, how many square miles are being lost per decade. So I am going to think of Glacier A as uh, well, since this is about time, I'm going to think of time as being the number of decades. Time in decades is going to be my x value, since that's my unknown quantity. And I can express Glacier A and I can express Glacier B in terms of this time. So Glacier A starts with an area of 40 square miles, but then every year, or I'm sorry, every decade, it loses a little bit. It loses um, 2 square miles per decade. And for Glacier B, it starts with a size of 32 square miles and then it gets smaller and smaller every decade at a rate of 0.25 square miles per decade. So times the time. And just like the other problems we've done, we're going to take each side of this equation and break it into its own separate equation. So I'll have f of x uh, minus, I'm sorry, equals 40 minus 2x. And my other equation will be g of x equals 32 minus 0.25x. Now, this is actually, given this problem, probably how I would have started. I actually would have started with two separate equations. I would have wanted to calculate kind of my y value here would have been the size of the glaciers. After a certain amount of time. And that might have been an easier place to start for some people, and that works totally fine. If that's a lot of times easier than writing one big complicated equation, is coming up with the two smaller, simpler equations. And so really kind of the slope intercept form where we knew the starting value of the glacier, 40 square miles or 32 square miles, and then we used the melting rate as our slope, and our x value is the time. So that is another way to approach coming up with this set of equations. All right, so the next step is to graph these equations here. So I'll do my purple graph first. My y-intercept is at 40, and I go down 2 for every 1 unit I move over to the right. Now that's going to be quite hard to graph on the scale that I have right now. It's going to be hard to grow to graph that scale, that slope of -2. So instead of thinking of that as being a slope of -2 over 1, I'm going to multiply the numerator and denominator by a value that will make this a little bit easier to graph. So if instead I focus on, let's say I want to go down by uh, 5 or even 10. If I want to go down by 10, I would have to go over 5 units to the right. So if I drop down to 30, if I go down 10, I'm going to go over to the right at the 5 marking right here. And if I repeat that process, go down 10 and 5 units to the right takes me here. So this is what one of my graphs looks like. And now I'm going to plot the green graph where I start at 32, which is probably around about there. And my slope here is negative 0.25. So my slope is negative 1/4. Again, it's hard to go down 1 unit and to the right 4. It's hard to go down one unit on the scale. But if I went down 2 units, I would actually be all the way at the 30 mark, which would be perfect. So if I go down 2 units, I have to go to the right 8. I'll just multiply the numerator by 2 and the denominator by 2. So the other point on my graph is over here. Now, when I've tried doing this before, oh no, it worked. I was worried it wasn't going to let me draw a sloped line. It's such a shallow slope that the computer sometimes assumes that it's actually flat. So I have an intersection point here, which I'd like to know the coordinates for. Now, for this particular example, the numbers don't work out to be nice and even. You may be better off trying this on a graphing calculator. So we're going to punch these values in and see what that looks like there. Well, as you can see, I have the wrong computer. I don't have my TI-84 emulator on this computer. So I'm using Desmos to try graphing these two lines. And right now I'm zoomed in too far to see the intersection. And this would happen on your graphing calculator as well. You would need to kind of judge the correct location to zoom in to actually see the intersection. And because the y-intercept is 40 and 32, those are kind of the values that I would use to zoom in on my graphing calculator window. Go from like 0 to 40 on the x-axis, 0 to 40 on the y-axis, to see if I can see the intersection. And then you would use the trace button to zoom in on a particular point. Now, if I click on this graph here, hopefully I'll get near the intersection point. And you can see that this intersection point does not have nice round values for the answer, not nice whole number answers. So if I were to round these values off to 2 decimal places, it would be 4.57, 30.86. And so those are the values that we'll plug in to look at what the answer to the question is. Based off of the graphing calculator, a reasonable approximation of that intersection point is 4.57 for the x value and 30.86 for the y value. Again, if you look at our original equations, it's the x value that's important. It's the number of years that's important, not the y value. So this x value is going to be the solution to my equation. 4.57 is the number of decades that will pass before these two glaciers are the same size. Now, the actual question that was being asked here was, in what year will the areas of the glaciers be the same? So we need to kind of convert decades into years and then go back and add that on to the 2020, our starting year. So 4.57 decades times 10 is 45.7 years. And if I add that on to the 2020 from the year when these measurements started being made, that gives us a year of 2065.7 or 2066 is our year. So that would be the final answer to this equation or this system. It's not really a system of equations until we split the equations apart, but to this equation of in what year would the area of the glaciers be the same. I hope this helps.